Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you need any help with homework or tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is the density of hexane in grams per centimeter cubed? Okay, so if you look at the MSDS of hexane, or in just some of its physical and chemical properties, you'll find that it has a density of 0.66 grams per centimeter cubed. Okay, so if we were to calculate for the density of hexane, we can do so by using the density equation. So that is my attempted symbol of density, which is just the rho, I believe. And density is equal to mass over volume. So depending on what you're given in a question, you can also calculate for the density of hexane, where mass is in grams, and volume can either be in centimeter cubed or in milliliters. And the junior tutor said that the density of hexane at 25 degrees Celsius, 660.6 kilograms per meter cubed. Converting the units to grams per centimeter cubed, we get 0.661 grams per centimeter cubed. So this solution is correct. Okay, so question number 2. What is meant by the term mole ratio? Give an example of mole ratio and how it is used in solving a stoichiometry problem. Okay, so let's define what mole ratios are. So mole ratios are the conversion factors between all of your products and reactants. Okay, so let's have an example. Let's say we had hydrogen, gas, plus oxygen coming together to form H2O gas. An important thing about using mole ratios and stoichiometry in general is to make sure that your reaction is all balanced. So in the case of this reaction, notice we have 2 oxygens on our reactant side and only 1 oxygen on our product side. So I'm going to write a 2 in front of H2O. And then next, you'll notice that there are now 4 hydrogens on our product side and only 2 in our reactant side. So I will put another coefficient of 2 in front of H2. Okay, so now everything is balanced. And let's say we had an example question. How many grams of oxygen is required to produce let's say 90.1 grams of water. Okay, so notice that both that we are looking for grams and we're also want to find out how many of these grams are needed to produce 90.1 grams of water. So even though everything in the question is related to mass, we still need to use mole ratios to answer this question. So the first step is to find the moles of water that is produced. So to do that, it's going to be number of moles is equal to mass over molar mass. So in the question, the mass of water produced was 90.1 grams, and the molar mass of water is 18.02 grams per mole. So if you're not sure how we found the molar mass of water, it is 2 times the molar mass of hydrogen, which is 1.01, plus the molar mass of oxygen, which is around 16. And you can just find these values on the periodic table. So if we divide 90.1 grams by 18.02 grams per mole, we end up with 5 moles of water. Okay, so step 2, we use mole ratios to find moles of oxygen required So if we wanted to produce 5 moles of water, this is when we would look at our balanced chemical equation, and you'll notice that 1 mole of oxygen is needed to produce 2 moles of water. So by using this mole ratio, then we can convert from moles of water produced to moles of oxygen that was required for the reaction. So if we divide 5 by 2, then you'll see that 2.5 moles of oxygen was required for the reaction. But for the last part of the question, or for the answer, now we need to find how many grams of oxygen is required. So step 3, find the mass. Okay, so pretty straightforward, since mass is just number of moles times molar mass. So now the number of moles of oxygen we found was 2.5 moles, and the molar mass of oxygen, well, O2, is 32.00 grams per mole. And again, we know this because 1 atom of oxygen has a molar mass of 16. So since O2 has 2 atoms of oxygen, its molar mass is 32. So this tells us that we need 80 grams of oxygen to produce 90.1 grams of water. Okay, so let's see what the junior tutor said. A mole ratio is a ratio between the amount in moles of two compounds involved in a chemical reaction. Moles ratios are the coefficients in a balanced equation. For example, the balanced equation for the combustion of methane in excess oxygen is the following. From the equation, we can see that 1 mole of carbon dioxide and 2 moles of water are produced for every mole of methane that is burned. Mole ratios are used as conversion factors between products and reactants in the reaction. The mole ratios will help us, for example, find the amount or mass of the products if the amount or mass of the reactant is given. Yep, so this solution is correct. Okay, so on to question number 3. What is the name of this hydrocarbon? Okay, so let's draw it out. We have 3 hydrogens attached to a carbon, another carbon, let's just draw it in the simple way so that it's less like big. Okay. So now in order to name hydrocarbons in general, we first want to find our parent chain. And then also number the carbons. And with naming things, we always want the lowest number possible when we add them all up at the end. So, for example, let's find the parent chain by circling the longest chain with the most important functional groups. So in this case, the longest chain is evidently here. If this side group was like 3 carbons long, then we would circle that part as the longest parent chain. But in this case, it's only a methyl group on this carbon, so we just need to circle this horizontal chain right here. And now I want to number the carbons, and I want the lowest number possible in my final name. So I'm not going to start numbering from here because this would make the methyl group on carbon 3, when I know that if I started numbering from here, the methyl group is on carbon 2, which is the lowest number. So we start numbering left to right. Okay, so after we found the parent chain and then we numbered the carbons, we want to identify all the functional groups or the side groups. So we'll see on carbon 2, there is a methyl group. So I will say that it is a methyl. And now we kind of have everything we need to name the compound. So we just name. So starting with the side groups first, I'm going to show that there is a methyl group on carbon 2. So the prefix is just 2-methyl. And then now I say my parent name. So since the parent is a 4-carbon chain, everything is single bonded. So we're going to use the root name butane. So this name is 2-methylbutane. Okay, so let's see what the junior tutor said. In naming hydrocarbons, compounds with only carbon and hydrogen, one must look at the type of bonds that exist. Yep, so everything was a single bond for our example. So this type of hydrocarbon is an alkane because it consists of only single bonds in the molecule. Alkanes have a general formula, CnH2n+2, where n is the number of carbons present in the molecule. In naming organic compounds, we follow the IUPAC system where alkanes end in the suffix -ane. The alkane is a branched alkane since it has a substituent attached to it. In branched alkanes, the IUPAC system prioritizes the longest continuous chain of carbon atoms in the molecule so that we can determine the parent name of the alkane. In this hydrocarbon, the longest chain is 4 carbon atoms. So a 4-carbon alkane is called butane. Now that we have determined the parent name of the alkane, we have to determine the name of the substituent. So the substituent is an alkyl group, meaning that it's just an alkane with a hydrogen atom removed to bond with the parent. So the substituent attached is CH3, which is a methyl. And we have to determine the number placement of the substituent in the chain. We do this by numbering the chain by beginning with the end of the chain near the substituent. So the methyl group is found in the 2nd carbon in the carbon chain. With this, we can now identify the hydrocarbon. The parent name butane is placed last, and the substituent group methyl preceded by the number designating its location on the chain 2 is placed first. Numbers are separated from words by a hyphen. Taking into consideration the rules discussed above, the name of this hydrocarbon is 2-methylbutane. Yep, so this solution is correct. Okay, so question 4. What is the conjugate acid of HPO4 2-? Okay, so let's recall what a conjugate acid is. This is the species that is formed after it accepts a proton. And we can also write the definition of conjugate base. As you can guess, it is the species formed after it donates a proton. Okay, so conjugate acid and conjugate base. So the question is asking for the conjugate acid of HPO4 2-. So let's write HPO4 2 minus. So conjugate acid is the species formed after it accepts a proton. So we are going to add a proton. And we end up with H2PO4 with a single negative charge. So in this case, HPO4 2 minus is our base, and H2PO4 minus is our conjugate acid. So bases are H plus acceptors. Okay, so the junior tutor said that the concept of conjugate acids and bases is an extension of the Bronsted definition of acids and base. Recall that a Bronsted acid is a substance that donates a proton, and a base is a substance that accepts a proton. So the conjugate base is the species that remains after the acid donates a proton, and the conjugate base is the species that is formed after the base accepts a proton. The conjugate acid of HPO4 2 minus is the species after it accepts a proton, or is HPO4 2 minus plus 1 proton. Thus, the conjugate acid is H2PO4 minus. Yep, so this solution is correct. Okay, so question number 5. What does each period in the periodic table correspond to? Okay, so each period in the periodic table corresponds to a principal energy level. So, in other words, the periods are the rows of the periodic table. Let's look at the periodic table. So you can see that all of the periods are shown like in this picture. So hydrogen and helium is a row, and lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, that is another, and so on and so forth. So with every new period row, there is a new shell. So for example, what they mean by that is if we had, let's say, fluorine, the inner shell contains 2 electrons, and then it has a second shell that contains the 7. Similarly, if we looked at an element in the same period as fluorine, such as neon, you'll see that it also contains 2 shells, but it has an extra electron making it have a full octet. But if we were to go to the next row down, which is period 3, let's look at chlorine. It has the inner shell, but this time it has an extra shell that is full. And similarly with fluorine, fluorine has 7 valence electrons as well. But notice that it is a row below fluorine, but they have the same number of valence electrons. So that's what this definition means, where each period in the periodic table corresponds to a principal energy level, which are the rows. So we can write the principal energy level of fluorine as N is equal to 2, neon N is equal to 2, and for chlorine N is equal to 3. Okay, so let's see what the junior tutor said. Each period corresponds to the successive occupation of the orbitals in an atom's valence shell. In other words, the principal energy level of an atom. For the valence shell, successive intervals down the table lead to successively higher values of N. First period of the periodic table, which consists of only helium and hydrogen, correspond to N equals 1. Second period from lithium to neon is N equals 2, and so on. The successive periods refer to atoms in which the shell of valence is outside of a center of inner completed shells and is more electron rich. Yep, so this solution is correct. Okay, just had to fix the lighting a bit. And we are on question number 6. What is the conjugate acid of H2O? Okay, so let's recall that conjugate acid is the species formed after it accepts a proton. And I'll write the definition of a conjugate base. Species formed after it donates a proton. Okay, so let's look at the example they give us. What is the conjugate acid of water? So let's say we had H2O plus a proton, since we're trying to find the conjugate acid. This gives us H3O plus. So our base in this case is the water. since it is a proton acceptor. And the species that was formed after it accepts a proton is the conjugate acid, which is H3O+. Okay, so the junior tutor said that finding the conjugate acid of water requires adding a proton ion to water. Conjugate acid of water is the hydronium ion, H3O+. Okay, so this solution is correct. Okay, so question number 7. How many electrons in an atom could have these sets of quantum numbers? Okay, so we need to find, pretty much all of the different possibilities or when you have a certain set of quantum numbers. So let's look at A. When n is equal to 3, the constraint with the quantum number for angular momentum, which is L, the only constraint is that it needs to be one less than our principal quantum number, which is n. So this means that our L value are all the values that are less than 3. So L can be either equal to 2, 1, or 0. So those are all of our L values. So this tells us that our magnetic quantum number values, which is ML, can either be equal to 0 or our ML value can be equal to -1, 0, or +1 if our L value is 1. And lastly, our ML value can be equal to -2, -1, 0, +1, and +2. So just depending on our L value, these are the possible angular momentum values. Okay, so recall that for each orbital, this can house 2 electrons. So let's pretend like we have, these are all orbitals that can house electrons. We need to count how many can have the quantum number, principal quantum number equal to 3. So I'm just going to draw the electrons in. So this is a full orbital with the 2 electrons pointing in either direction. And then let's fill up all of them and then count up how many electrons this is. This isn't how you fill it up, by the way, but I'll show that in the next example. But this is, let's say, all of the orbitals are filled, so the max number of electrons that you could get when n is equal to 3 is 18. Do it in a different color. Electrons and have this set when n equals 3. Okay, so let's do the same thing for part B. N is equal to 5. And this time they specify that L is equal to 2. So we're only really concerned about the ML values ranging from -2 to +2. So let's draw them all out again. And then I'm going to show all the orbitals. And then draw out the electrons. So when we fill out electrons in the orbitals, we want them to all be facing the same direction first. So this is how you would fill it up. And then once you continue and add more electrons, this is when you would show them going in the opposite direction. So that's how to properly fill in the orbitals. I didn't do that the first time. And if we count it all out, then we can see that 10 electrons can have the set n equals 5, L equals 2. And then lastly, we have n equals 6, L is equal to 3. And this time they really specify that our ML is only equal to -1. So since we're only interested in the ML value, I'm going to draw out its filled orbital, and it's only the 2 electrons. So therefore, only 2 electrons can have this set of quantum numbers, since it really specifies what the ML value is. Okay, so these are all of our answers. And now we can see what the junior tutor said. These are 4 quantum numbers. Oh, there are 4 quantum numbers. Principal, which is n, angular momentum, which is L, magnetic, which is ML, and electron spin, which is MS. The following is what the quantum number tells in brief. N tells us how large the electron is. L tells us the shape of the orbitals. The shape of the orbitals and their corresponding L values are S, P, D, F, G, and so on for 0, 1, 2, 3, and so on. So it only really goes up to F, but that's okay. ML describes the orientation of the orbital in space, and MS tells us where the electron spins clockwise or counterclockwise. The possible values for each are tabulated below. So these are all the possible quantum numbers, and then these are the allowed values. So the n has to be greater than 0, so it goes 1, 2, 3, and those correspond to all the rows in the periodic table. And then L can range from 0 to n minus 1. Our ML value ranges from our -L to +L. And then finally, for the electron spin, it can either spin clockwise or counterclockwise, and we denote it as either positive or -half. Okay, so part A, since n is equal to 3, the L values are 3. I think they mean 3. Oh, okay, so 3 minus 1. That means that the L values are from 0, 1, and 2. This corresponds to the S, P, and D subshell. The ML values are 0, -1, 0, and 1, and -2, -1, 0, 1, and 2. Each value corresponds to 1 orbital. Each orbital can have 2 electrons. That means that for n equals 3, there are 18 electrons that can have this set. Part B, for this set, even though L can have other values, we only considered L equals 2. ML values are -2 to +2. Each value in the set is an orbital. Since each orbital can have 2 electrons, there are 10 electrons that can have this set. Lastly, our last question is much more specific. We are only concerned with ML is equal to -1. This is a single orbital that can accommodate only 2 electrons. Yep, so this solution is correct. Okay, so question number 8. Why does ice float on water? Yep, so this is a pretty common question. Let's draw out a diagram. This is a glass of water. And you can typically observe your ice cubes, and they always want to float to the top for some reason. And usually when we have like solids in a liquid, they just sink like straight to the bottom. But in the case of ice, they float on the surface of water. So this actually has a reason, and this is because water achieves its maximum density when the temperature is around 4 degrees Celsius. So therefore, when we have at 0 degrees Celsius, when it freezes to ice, ice is less dense than water. Okay, so we can think about the density equation, where density is equal to mass over volume. When we have an ice cube, its mass is kind of less than if we had the same volume. Where is it going with this? Yeah, so if we had like the same volume of ice versus water, like if they both took up like 5 milliliters of space, then the mass of the ice is lighter than the mass of the liquid. That's what that means by less dense. And the junior tutor said that ice floats on water because ice is less dense than water. Equation 1 shows the formula for density, where rho is the density of the substance, mass is the mass of the substance, V is the volume. Ice is less dense than water because when water freezes, it conforms to a lattice structure where the water molecules are farther apart than in liquid water. Because of this, there is more space in the structure in ice, and its volume increases. The increase in volume means that its density will decrease. Yep, so this solution is correct. Okay, so question number 9. How do you calculate the freezing point depression? Okay, so freezing point depression. So the freezing point depression is when you have a decrease of the freezing point of a solvent when you have the addition of a non-volatile solute. So it can be calculated using the pure solvent's freezing point and molality. Okay, so I'll show the equation. So the freezing point depression is equal to molality, which is moles per kilogram of solution, times Kf times I. So Kf is known as the cryoscopic constant. So again, this varies depending on the solvent that you have. So it's the pure solvent's freezing point. And I is something called the Van 't Hoff factor. So this depends on how many ions that are present in the solution. Okay, so the junior tutor said that the freezing point depression is the difference between the freezing point of the pure liquid and the freezing point of the solution. Okay, so they showed delta TF and how it came to be. And then we can also relate the freezing point depression to the molality of the solution. Okay, so they have Kf times m. Kf is the molal freezing point depression constant of the pure liquid, and m is the molality or the molal concentration of the solution. Okay, so I'll also note that, okay, so this solution is correct. And then I'll just also add that the Van 't Hoff factor can also affect the freezing point depression value. Okay, so question 10. Okay, so they give us all the different acids association constants, so Ka, of certain acids. Using the Ka for these acids, calculate the Kb for the following ions. So, which is the conjugate base. So, first I'll write the expression of Kw, which is the ionization constant of water, and it is equal to your Ka value times your Kb value. Okay. So that is pretty helpful. And the kW value has a value of 1.0 times 10 to the negative 14. So since we know the value for kW and we're given the value for Ka, then we can calculate the Kb of all of the conjugate base ions for the acids. So it's pretty straightforward. So let's look at A first. For the first acid, AB, I'll just rewrite the equation, is equal to Kw, which is 1.0 times 10 to the negative 14, divided by the Ka value, which is 1.8 times 10 to the negative 5. So for this Kb value, you should end up with 5.55 times 10 to the negative 10. Okay, so let's do the same thing for the second acid. Its Kb value is equal to Kw divided by Ka, which is 4.3 times 10 to the negative 7. And you should end up with 2.33 times 10 to the negative 8. Okay, so let's see what the junior tutor said. The relationship between Ka and Kb, an acid and its conjugate base, is shown in equation 1. Okay, so Kw is equal to 1 times 10 to the negative 14, Ka times Kb. So to calculate the Kb of the conjugate base, we divide Kw, or the auto-ionization of water, by the Ka. Calculations are shown below. So they showed 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5 gives 5.55 times 10 to the negative 10. Next, for CO3 minus, we have 1 times 10 to the negative 14 divided by 4.3 times 10 to the negative 7, and they got 2.1. That's a bit off, but almost the same, times 10 to the negative 8. So maybe there's a bit of a calculation error, but I'll still say that this solution is correct. And explanation. Okay, so that is all for this session for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and leave it a thumbs up and comment, and you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.